All right, to make sure we stay on track, let's go ahead and get this ball rolling. Just like the previous one, if you were here for that, you can feel free to interrupt me with questions anytime, ideally to keep them somewhat related to the topic I'm discussing so I don't jump all over the place and can keep us on track, but I'm happy to pause for tangential questions even if it's not exactly the problem that I'm going over. And of course, if you have to leave early, feel free to do that. There's no reason you have to stay at the end. This will be recorded and put onto YouTube later today, so you'll be able to view it on your own time. All right, so the first thing I'm going to do before I jump into the problems is I'm going to go over, I'm calling it a review, although maybe that's not accurate because I didn't actually cover this very much in class. So it's just a quick, it's in the textbook, but I sort of glossed over it in class. Something about the shape of hybrid orbitals. There's a few exam questions that, again, depending on luck with the draw, you may or may not encounter, that asks you to identify hybrid orbitals based on their shape, or at least say something about the shapes of them. So we're talking about an individual hybrid orbital, which would be sp, sp2, or sp3. The other ones are more complex, and we're not going to deal with their shapes. Remember what we're doing is we're taking an s orbital, which has a spherical shape, and combining it with either 1, 2, or 3 p orbitals, depending on whether it's sp, sp2, or sp3. But it's these hybrid orbitals are, you can think of them as sort of a blend of an s and a p. And then what you end up with for all of these, and there's slight differences between sp, sp2, and sp3, but we just want to know the basic shape of all of them, which is you can think about superimposing these two, and remember that the phases that are opposite are colored differently. So you're going to put this s orbital on top of the p orbital, and the phases that are opposite are going to partially cancel each other out because they're opposite in sign, and then the phases that are the same are going to reinforce. And what you end up with is it has two lobes, but they're unequally shaped. So something like this would be an sp or sp2 or sp3 hybrid. Again, slight differences between the three that we're not going to worry about. But you get these sort of shapes where it's two lobes, kind of like a p orbital, but the lobes are not the same size anymore. So if we ask you about the shape of an individual hybrid orbital, that's sort of the picture and the description you want to have in mind. And then if we ask you about the arrangement of a set of hybrid orbitals, and that's going to depend also on whether you're talking about sp, sp2, or sp3, you look at how these hybrid orbitals are arranged in space. And so if you have 4 hybrid orbitals, all the same, but they're jutting out in 4 directions in a tetrahedron, you would know that that's the sp3 set of hybrid orbitals. So it's 4 of these individual orbitals arranged in the 109.5 degree angles from each other that you would have in a tetrahedron. If you have 3 of them in a plane that's 120 degrees apart for each of them, that's going to be your sp2 arrangement. So you have 3 identical hybrid orbitals arranged around a triangle. And then the ones that are 180 degrees apart would be 2 of these opposite each other to make an sp set of hybrid orbitals. So if you're asked to identify a set of hybrid orbitals based on the shape, it of course comes down to the shape that corresponds to that hybridization being linear, trigonal, planar, or tetrahedral, and the 2, 3, or 4 hybrid orbitals that you need will arrange themselves in that orientation to make those types of shapes. So just a quick rundown of shapes, which I didn't really go over in class this time because of some time constraints. So any quick questions on that before we get into the problems that we are going to go through? All right, so if not, we will move on to the first question now, which is dealing with VSEPR. So we want to know the electron group arrangement and molecular geometry for the anion SeF3-. All right, so to review Lewis structures, anytime we're dealing with VSEPR shapes or hybridization, those two topics that come up in the first part of this test, we have to be able to draw a Lewis structure first, so we'll review the process for doing that. The first step is to count valence electrons for each of the elements. So let's open up our periodic table. All right, so we have selenium and fluorine. So selenium Se is down here. It's in group 6, so it's going to have 6 valence electrons. And then fluorine, as we know by now, is in group 7, so it will contribute 7 valence electrons. So we're going to count those. We have 1 selenium in the formula. It's going to include 6 valence electrons. We have 3 fluorines, F3, so it's going to be 3 times 7 for fluorine. And then we can't forget that we have a negative charge overall in this ion, so that's going to add 1 extra electron to the mix. And so we get a total of 28 electrons. So when we're drawing a Lewis structure, we need to know how many valence electrons we are going to use so that we can figure out how to arrange them around the central atom and all the outer atoms. So we start with single bonds to all of the fluorines from the central atom selenium. We complete the octets of fluorine. So this is still technically a review of exam 1, but you're going to have to be able to do this as well here. And then finally, we've done 3 octets. So each of these 3 fluorines now has 8 electrons around it, 2 from the bond, 6 lone pair electrons. And that leaves, that's 24 of our total. So we have 4 more that go in the central atom. So we get 2 lone pairs on selenium. So that's our Lewis structure. We don't necessarily have to worry about formal charges, double bonds, and things like that if we're doing VSEPR. This would be where we would stop anyway, because we should recognize the pattern by now that we never draw double bonds to fluorine. So we don't have to add any double bonds, and even if we did, it wouldn't change our prediction about the shape anyway. So we get this structure, and we can translate this into the AXE notation if that's what you prefer to do. So we have our central atom. There are 3 fluorines bonded to it. That we can tell from the formula of the compound, which is SEF3. But then we also determine that there's 2 lone pairs on the central atom, so that makes it AX3E2. And then if we're going to determine the 2 VSEPR classifications for this, so one of those being electron group arrangement and one of those molecular geometry, the electron group arrangement depends on the total number of electron groups, or what we often refer to as steric number. Or at least that's how I was taught it back in the day. So we have a total of 5. We have 3 atoms and 2 lone pairs in the central atoms. That's a total of 5 electron groups. And so anytime you have 5 electron groups, any combination of atoms and lone pairs, that's going to give you the same electron group arrangement, which is going to be trigonal bipyramidal. So trigonal bipyramid is going to be the electron group arrangement anytime you have 5 electron groups, which could be AX5, AX4E, AX3E2, AX2E3, a lot of combinations that all have a total of 5 and all have the same electron group arrangement. That's the arrangement of all 5 of these groups. But then if we want to talk about the molecular geometry, we have to consider the lone pairs and how those affect things. And the molecular geometry is going to basically look at what shape do the atoms make up, ignoring the lone pairs. So if we draw the 5 electron groups, we have a trigonal bipyramid, which is a triangle with a flagpole coming out above and below. We have 5 electron groups, and whenever we put lone pairs into these structures, for 5 electron groups, the lone pairs always go on the triangle, onto the base of the trigonal bipyramid, and that leaves these positions with fluorines. And if we draw that bond in explicitly, I think we can see that that's turned on its side, but that's going to be our T-shaped arrangement. So AX3E2 will give you T-shaped, where you have 5 electron groups, and the 3 atoms bonded to the central atom make up what looks like a T if we were to rotate this 90 degrees. So trigonal bipyramidal is the electron group arrangement, and T-shaped is the geometry, so that's going to be choice C, which has both of those correct. All right, so questions on VSEPR or the difference between electron group arrangement and molecular geometry, anything along these lines that I should highlight for you or go in more detail? All right, if not, we'll keep going then. All right, so our next one is asking about polarity, which is very much related to the molecular structure. So we need to get the molecular structure for all of these two to figure out if they're polar. So if we have this type of molecule, so what we notice for all of these molecules, they're all fluorides, but in each case we have a central atom and we have just one type of atom bonded to the central atom. So NF3, BF3, XEF2, XEF4, SF4. So in that situation, the AXE notation, or the molecular geometry, is going to tell us whether or not it's polar or not. So here we're looking for one that has a non-zero dipole moment, so that's a fancy way of saying that it is polar. So we're looking for the polar molecule in all of these, or some combination of these that would be polar. And there are some that are pretty easy to look at. So when you're sort of sorting through answer choices like this, remember that if you have 0 lone pairs, so in other words, the geometry is AXME0 or just AXM with no lone pairs. In this situation, you would expect it to be nonpolar. Now that's only true if all the X's are the same, so don't abuse this shortcut. But in these situations, we only have fluoride as the outer atom. So in any of these compounds that don't have lone pairs, they will be nonpolar. If any of them have one lone pair, which would be AXME, so there's a few possibilities there, AX2E, AX3E, AX4E, AX5E, we had all of those as possibilities. Anything with one lone pair, though, you know is going to be polar. And that it actually doesn't matter whether all the x's are the same or not. If it's one lone pair, it's going to be polar. If they have 2 or 3 lone pairs, there's a couple of each, so we have to think more in depth about the geometry. But these two you can definitely look for in problems like this to know that if there are 0 lone pairs, it has to be nonpolar. If there's 1 lone pair, it has to be polar, and that can help you sort through, in many cases, a lot of the answer choices, if not all of them. All right, so we're looking for the ones that are polar, so we do need to quickly do the VSEPR. So I'm not going to go through all the steps again, but if we were to work through them on our own, we would see that NF3, which is our first answer choice here, I don't have to circle that yet, NF3 ends up as AX3E, so we would get this sort of geometry if we draw it in 3 dimensions. It's pyramidal in shape, and whether we appreciate the shape in full or not, anything with 1 lone pair, as we said, is going to be polar. So this AX3E structure, which is pyramidal, would give us a polar geometry. Our next choice is BF3. So even though it has a very similar formula, when we draw the Lewis structure for this one, we end up not having a lone pair in the central atom. It's just going to be boron with 3 fluorines. Remember that boron is one of the ones that doesn't typically have complete octets. So in this case, it's going to only have 6 valence electrons, but for boron, that's fine. And so we end up with this one is AX3. And as we said, anything that has 0 lone pairs in this sort of situation would be nonpolar. For XeF2, and remember that another one that's helpful to think about both in the context of VSEPR determining the shape as well as for polarity is that if you have 2 atoms bonded to your center atom, there's only 2 possible geometries. Does anybody remember what they are? So 3 things. Linear and bent. So those are your only 2 options. Linear would be nonpolar, bent would be polar, because in linear the 2 dipoles are opposite each other and cancel each other out. In bent, they're not completely opposite, so they don't completely cancel. So for XeF2, we have just 2 atoms bonded to our central atom. We need to figure out if it's linear or bent. And what we come up with for XeF2 is it's going to end up being AX3E2. So it's going to have 5 electron groups. And what we do in that situation, as we said, is for 5 electron groups, we put lone pairs on the triangle. We end up with the fluorines opposite each other. This is going to be AX2E3. It's linear, and because it's linear, it's going to be nonpolar. Okay, so anything that's linear would be nonpolar. The linear geometries being AX2 and AX2E3. So that's nonpolar. And then we have XeF4. This one is one that's not as obvious, but this one ends up being square planar. So if we draw a square of 4 atoms, this is AX2E2. I'm not showing the lone pairs here. I'm going to draw the plane of the square sort of in the plane of the page. The lone pairs would be coming out towards you or going into you. But in the square planar geometry, your individual dipoles all cancel each other out. So we have 2 fluorines that are 180 apart. Those dipoles cancel. The ones horizontally cancel. So this is AX4E2, sorry. AX4E2 is square planar, which is going to be also nonpolar. As I said, with 2 lone pairs, it's not as obvious, but this is one that's nonpolar where the dipoles cancel. And then the last one we have is SF4. So SF4 is a geometry that we mess up a lot, but again, if we at least draw the Lewis structure correctly, we would find that SF4 is AX4E. The geometry for this is seesaw, but regardless of whether we remember that name or not, 1 lone pair means that it has to be polar. Okay, so it just has a single lone pair in the central atom, making it polar. So if we sort through all of these, we're looking for the ones that have non-zero dipole moments. I shouldn't have circled that one. We want the ones that are polar in this case, which is going to be this one and that one. So just those 2, and F3 and SF4. Both of those have 1 lone pair, so as we said, anything with 1 lone pair is polar. The rest of these, some of them have lone pairs, some of them don't. They're all nonpolar though. So there is a table in the notes from this section that sort of summarizes this. Like I said, most of them are pretty easy to pick out if they have 1 or 0 lone pairs. There's about 4 geometries that have 2 or 3 lone pairs that you have to be able to sort through a little bit separately from that. All right, questions on this one or molecular polarity in general? Yes? So the name for this one would be called seesaw, which is not obvious from how I drew it, but if you turn it on its side, that's what it looks like. So we call that seesaw. It's one that's commonly missed, but for this type of problem, as long as you know it has one lone pair, you would still predict that it's polar either way. Okay, anything else? All right, on to the next one then. All right, now we're moving on to hybridization. We already drew this anion, so we don't have to go through the steps of drawing it again. So we have that same SEF3 minus anion. We want to know what's the hybridization of the central atom. So as we saw before on the first problem, SEF3 minus has the AX3 E2 electron arrangement, which we said gave it a T-shaped geometry. But what determines hybridization is not going to be the molecular geometry, but the electron group arrangement, the steric number. So as we saw, the steric number on this one, which gave it a trigonal bipyramidal electron group arrangement, was 5. And so anytime we have a steric number of 5, we predict a hybridization. That means we need to have 5 orbitals hybridized. Okay, so if there's 5 electron groups, we have to hybridize 5 orbitals to be able to attach them to the central atom. And to do that, we say that in these types of molecules, the orbitals that are available for hybridization are going to be an s orbital, which is one of the valence orbitals, 3 p valence orbitals, and if needed, we can hybridize up to 2 d orbitals. So those are the possible orbitals that we have for hybridization. If we have 5 electron groups, we have to hybridize 5 of those, and so that would take these first 5 here. 1, 2, 3, 4, 5 orbitals to hybridize, and what that leaves us with is s, p3, and then d. Sometimes written as dsp3, so don't think that those are two separate things. They're the same thing, just written slightly differently. So you might see it as dsp3, but it's a total of 5 orbitals hybridized, and we make them as we know that as sp3d or dsp3. So whenever you're predicting hybridization, all you need to know is the number of electron groups, or what I said I refer to often as the steric number. So depending on the number of electron groups you have bonded or attached to the central atom, that's going to dictate the hybridization. So the possibilities are 2, 3, 4, 5, and 6 electron groups when we're dealing with hybridization. And this number of electron groups tells you what it would be. So 2 electron groups is sp, we hybridize 2 orbitals. 3 electron groups is sp2, we hybridize 3. 4 electron groups is sp3, we hybridize 4. As we just saw, 5 electron groups is sp3d. And the highest we would go is 6 electron groups, which means we need 6 orbitals, sp3d2. All right. So predicting hybridization is really just a factor of how many electron groups are on the central atom. So all of these things end up being sort of related to each other. The electron group arrangement, the geometry, the hybridization, the polarity, all of those are kind of linked by what the molecular shape and the electron group arrangement are. And so being able to practice all of those as you do these, kind of go through all those aspects is going to be helpful as you prepare this section of the course. All right, any questions on this? All right, the next 2 questions, I believe, deal with molecular orbital theory. So when we're talking about hybridization, the bonding theory that is associated with is called valence bond theory. And that, again, assumes that we have these sort of mixed hybrid orbitals on the central atom, and they overlap with orbitals from the outer atoms to make bonds. The other bonding theory we covered... No, don't go away. Stay there. All right, good. The other bonding theory that we covered was molecular orbital theory. And molecular orbital theory, we're going to only deal with it for diatomic molecules, so molecules that have just 2 atoms in it, so nothing more complicated than that. And on the test, what you'll see is there's going to you can expect to have 2 questions dealing with molecular orbital theory. One of them will deal with relatively basic orbital diagrams or some conceptual questions like this one, and the other question would be the more complex orbital diagrams that deal with both s and p orbitals. So there's kind of, a combination of different things we can ask you on this. And in this question, what we're looking for is, according to molecular orbital theory, which of the following will increase the bond order in a diatomic molecule? So as we recall, when we're doing with molecular orbital theory, we draw these orbital diagrams that arrange the molecular orbitals from lowest to highest. We fill them with the correct number of electrons, whatever that molecule ends up having. And then we can answer some questions about that, like bond order, number of unpaired electrons. So this question is dealing with this bond order. So once we know the arrangement of the electrons, once we know the electron configuration of that molecule, the bond order is given as 1/2 times the number of bonding electrons. So the number of electrons that end up in bonding orbitals. Half of our orbitals are going to be bonding, the other half are going to be anti-bonding, and if those have electrons in them, you subtract that from the bond order. Okay, so bonding electrons minus anti-bonding electrons once we know the configuration. So then if we're looking at which of the following will increase the bond order, from a mathematical standpoint, if we want the bond order to get larger, we need to either increase this term here by adding electrons to bonding orbitals. So if we add an electron to a bonding orbital, that's going to make the bond order go up by 1/2 for each electron that we add. So remember, bonding orbitals are orbitals that have electron density in between the two nuclei that are bonded. So every time we put electrons in there, we're drawing the nuclei closer and closer together with a stronger attraction. So adding electrons to bonding orbitals, both mathematically and conceptually, we can see that the bond order will increase in that case. We're going to make the bond stronger when we add electrons. But then based on the second term of the equation here, we're subtracting the number of antibonding electrons, which means every time we have electrons in antibonding orbitals, we make the bond order smaller. So if we want to make the bond order bigger, we would need to remove these electrons. So if we add electrons to an antibonding orbital, we're going to actually decrease the bond order. This one is looking for the ones that will increase. So adding electrons to antibonding orbitals decreases the bond order. If we make this term larger, the overall bond order becomes smaller. But if we remove electrons from antibonding orbitals, that's another way for the bond order to go up, because antibonding electrons weaken the bond. If we have less of them, we're weakening the bond by less, so we're making it stronger. Sort of an addition by subtraction scenario in that case. Okay, so the four answer choices, we see that adding electrons to a bonding orbital will increase the bond order. Adding electrons to an antibonding orbital, as we saw mathematically, is going to decrease it, so we don't want to pick that one. Removing an electrons from a bonding order would decrease this term and make it smaller also, so we don't want to pick that one. But then removing electrons from an antibonding orbital will increase the bond order by decreasing the second term here, so that would be another one we would choose. So of these two choices, A and D, two of them, are going to be operations that will result in an increase in bond order according to molecular orbital theory. All right, so that one kind of dealt with one of the concepts involved with MO theory. So any questions on this or related topics? All right, so then the next question that I have here, the next problem, is one that has more of the sort of practical bent to it, where we're going to actually have to populate orbital diagrams and answer some questions about it. So this asks us for both. That's really the two things we could ask you about, which is the bond order and number of unpaired electrons for this cation here. And so again, if you see a diatomic molecule or a diatomic cation, and we're asking you about bond order, number of unpaired electrons, you should immediately zero in on this being a problem involving molecular orbital theory. So what we have to be able to do then is arrange the orbitals from lowest energy to highest energy. So in class we drew the orbital diagrams, and we showed how atomic orbitals on each atom mix together to make bonding orbitals, which are lower, antibonding orbitals, which are higher. The important part for you to answer these questions is to remember what order all of those molecular orbitals come in. So if we're dealing with oxygen, which is in the second half of the p block, so anything from oxygen, fluorine, neon, those last three p block elements, the ordering is as follows. So we have our sigma 2s on the bottom, followed by sigma star. So the 2s orbitals come at lowest, sigma and sigma star, bonding, anti-bonding. And then in the p orbital levels, this is where we have a little bit of variation. For oxygen, the sigma 2p comes first, and then pi, so the two bonding p orbitals always come first, they're at lower energy. And then we have pi star and sigma star are always the last two, so the anti-bonding 2p orbitals come last. All right, so we do have to remember in some cases that it's these two orbitals here that sometimes switch. If we were in the first half of the p block, pi would come first and then sigma. It doesn't really matter for determining the bond order whether you switch them or not, but for number of unpaired electrons they need to be correct. All right, so we have this orbital diagram. Again, we showed in class where these orbitals come from. So we had, if we want to draw the more complete diagram, we have the 2s and a 2s mixing together to make the sigma and sigma star. We had our three 2p orbitals that combined to make all of these. So that makes I'm not going to draw that in because that makes the diagram more complicated. What you need to be able to do for this, as I said, is just know the order that these molecular orbitals come in and then fill them with the correct number of electrons. All right, so this is now just a lot like we did for atomic electron configurations. For atomic configurations back in Chapter 2, we used the periodic table to tell us what orbital all the energy levels came in. Here you kind of just have to know it or remember it. And this is the order that the orbitals come in. We have to figure out how many electrons there are. I have a typo that I've still never fixed, which should be that a cation, not action. Autocorrect, I'll blame it on that, I guess. And so we have O2 plus cations. We need to find the number of electrons. We have 2 oxygens. Oxygen is in group 6 of the periodic table if you find it, so that's going to be 2 times 6. But then we have a positive charge, so we subtract 1. So we have 11 total valence electrons. So counting valence electrons for MO theory is the same as we've always done it. You just look at the periodic table, add them up, account for any positive or negative charges. So we have 11 valence electrons. For valence bond theory, drawing Lewis structures and things like that, it's hard to deal with odd numbers of electrons, so MO theory is especially valuable for that. And then we're going to put these into the diagram, lowest energy to highest energy, filling up with 11 electrons. So just like atomic configurations, we go lowest to highest. We put 2 electrons into each orbital. So that's 1, 2, 3, 4, 5, 6. When we fill the pi orbitals, there's 2 orbitals at the same energy, so we go one at a time. 7, 8, 9, 10. And then our 11th and final electron goes up there in pi star 2p. So we go lowest to highest energy, and we always fill them in that order. If we wanted to write the configuration for this, we would have sigma 2s with 2 electrons in it, sigma star 2s with 2 electrons, then sigma 2p has 2 electrons in it, pi 2p has 4, the pi levels can hold up to 4 electrons, and then our pi star 2p has 1 electron in it. So this would be the electron configuration for this. We didn't really ask for that here, but this is another way that you could write it out or see it asked on questions. Yes? Yeah, so you might have a question where it asks you for what is the electron configuration of this cation, and this is the answer you would then pick, if that was what it was asking. So that is a possibility. The more common ones are going to be dealing with bond order and unpaired electrons like we do here. So once we have the diagram and the configuration, we can calculate bond order by, again, using that same equation, 1/2. Then we take the number of bonding electrons. So bonding electrons are the ones that are in orbitals that don't have stars next to them. So that's going to be 2 from down here, 4, 6, 8. So 8 of our 11 electrons are in bonding orbitals. And if 8 of the 11 are bonding, that means the other 3 must be anti-bonding. So we have 1, 2 here. The last one up here is also an anti-bonding orbitals that have asterisks or stars next to them. So 1/2 times 8 minus 3 gives us a bond order of 2.5. So whenever we have odd numbers of electrons, we will predict a fractional bond order of either 0.5 or 1.5 or 2.5. And then if we look for number of unpaired electrons, we see that the only unpaired electron is the one in the very last orbital, the very last one we put in. So these 2 are paired here, but this one is unpaired, so there's going to be 1 unpaired electron. There is a slight shortcut you can take, although if you're worried about forgetting the shortcuts, then maybe don't bother with it. But if your molecule has an odd number of electrons, like this one does, or this cation has odd number of electrons, it will have to have 1 unpaired electron. That's the only way it can be. If it has an even number of electrons, it could have 0 or 2, so you have to draw out the diagram to figure that out. If there's odd numbers of electrons, it's going to be 1 unpaired electron. That's something you can know right off the bat. Because no matter how you arrange an odd number of electrons in here, one of them will end up unpaired. Okay? But that's how we would deal with this one, drawing the full configuration and getting those 2 pieces of information out of it. Yes? The bond type for this would be a little bit hard to answer, but you would, so the 2 sigmas would cancel each other out from the 2s. You would have 1 sigma bond from the 2p, and then for the pi orbitals, you have 2 bonding orbitals that are filled, so that would give you 2 pi bonds, but then you're partially canceling out one of those. So basically you have 1 sigma and 1.5 pi's. So we don't really deal with half bonds in the other bonding theories, but for MO theory you could predict half bond orders, which means in this case it would be a sigma and 1.5 pi's. But we wouldn't really ask you that for an odd numbered species. For even number ones you might have to answer those types of questions, but it's a little bit more confusing for these odd numbered ones to have these half bonds, as we call them. Yep.
Do we really know how to do the MO diagram for the heteronuclear ones that aren't adjacent to each other?
So heteronuclear diatomics, so what he means by that is diatomic molecules that have 2 different elements, and you would potentially have some questions about those, but we will tell you what order the orbitals come in. We'll either tell you that they follow the orbital diagram for nitrogen, which is has these two flipped, or the orbital diagram for oxygen like I drew here. So we would specify the order if it's important for the question. But you might have to still deal with those, but again, in that case, you just need to know the total number of electrons, dump them into the diagram, and then answer whatever question is asked in exactly the same way we did here. Yep. Boron and then carbon and nitrogen, yes. Yeah, so the first half of the P block, yes. So P1, P2, P3, that first half, you would have these two orbitals inverted relative to each other. And then the second half of the P block, it follows this order here, okay? Usually doesn't matter, but like I said, for number of unpaired electrons, you need to make sure you have that ordering correct. All right, anything else? Okay, let's move on then. All right, now we're into, if you're keeping track of where we are at home, we're in the chapter 5 material analysis. We've moved on to things dealing with molar mass, moles, all that kind of good stuff. So here we have a hypothetical element with an atomic mass of 132.2145, which just coincidentally has my initials. If it has two stable isotopes, 131 and 134, we want to know what is the percent abundance of the heavier of the two, 134. So anytime we're dealing with atomic mass, the definition of atomic mass, isotope abundances, those are all related to each other. The one sort of mathematical equation we want to think of, the relationship, is that the atomic mass, and this pen keeps putzing out halfway through. I'm going to back up. All right, so the atomic mass is given by the abundance of each isotope, the fractional abundance, multiplied by the mass. So if we have two isotopes, A and B, let's say, or in this case, 131 and 134. So it's going to be the abundance of the 131 isotope times its mass plus the abundance of the second isotope times its mass, which I'm running out of room because I didn't plan this well, 134. So here we have two isotopes, so the atomic mass is going to be the fractional abundance of each isotope multiplied by the mass. Now if we had more than two isotopes, you would just keep adding them on and on and on until you use up all your isotopes. For problems like this where you're solving for an unknown, we would cap it at two isotopes. But if you were solving for atomic mass just using this equation, having more than two isotopes would be a possibility. But here what we're solving for is percent abundance of the heavier isotope. So we have to look at what's in the problem. So the atomic mass here is given to us. We have unknown abundances. We're not telling you anything about the abundances. So we're going to call these our variables x and y, or whatever you prefer to call them. So that's going to be x and y. And then the two isotope masses are also given. So the mass of the lighter isotope is here, 130.9856. So that's also given. And the mass of the heavier isotope is also given. So we have the two masses. We don't have the two abundances. Remember, whenever we're dealing with problems like this, and especially when we're solving for an unknown abundance, we have to remember that the sum of the abundances as fractions will equal 1, or alternatively the sum of the percent abundances would equal 100. So we have two of them in this case, so they add up to 1. And that means that we can rewrite this variable here, x, as 1 minus y, and then plug that into this equation up here. So putting the numbers in now, we see that our atomic mass, which is given to us as 132.2145, that's going to be equal to the mass of the first isotope, 130.9856, times its abundance, which we said was x, plus the mass of the second isotope over here, which in the problem is 133.9767. So all the numbers in this problem that we have so far are all given in piece of information, times the abundance y. And then we're going to replace x with 1 minus y. We're solving for y here, so that's why I'm doing it this way. You could have also done it the other way, but then you'd have to remember what we're referring to. So we're looking for the abundance here of the heavier isotope. So the most efficient way to do this problem is to solve for y directly. If you solve for x instead, you just have to go back and find y using this relationship here. So when we solve for y, I'm not going to go through all the algebra, but it's we'll We plug in and we get 132.2145 is equal to 130.9856 times 1 minus y when we make the substitution there, plus 133.9767 times y. So we have a linear equation with one unknown. And that means y, which is the abundance of the heavier isotope 134, what I got was 0.4109, and then the percent is just the fractional abundance times 100. So it's that number, 09, times 100, which ends up becoming 41.09%. Okay? So remember, whenever we're dealing with percent, you have to take your fraction and multiply it by 100. So don't forget that definition, because usually when I look through problems like this on the exam, there's going to be at least a few people each time that answer with just 0.4109, which means they did the problem correctly, except for the very last step, which is potentially the easy step of multiplying by 100. So anytime we ask for a percent, remember to multiply by 100, and typically you won't have percents that are too small. I mean, you know, I guess it could be variable, but you would expect the percentage to probably be between 1 and 99. If you get a percentage that's like really small, you probably mess something up. If you get a percentage that's above 100, well then clearly you mess something up. But remember to also always do that step of multiplying by 100 whenever a percentage is what we're asking for. All right, questions on this? All right. All right, so now we're dealing with mole conversions. So there will be some problems where it's just requiring us to convert different quantities into moles, whether it be masses like we have here or molarity, which we'll see probably later on. And so what we're looking for here is how many moles of sodium ions are present in 65.65 grams of sodium phosphate. So a lot of the problems in this section dealing with mole conversions or chemical reactions in stoichiometry, we do have to be able to take the name of a compound and produce the formula. Because anytime we want to deal with moles, we have to know what the formula of the compound is. And so if we're not giving you the formula, you have to make sure you remember the stuff we learned earlier about how to take the name and go to formula. So sodium phosphate is an ionic compound, so we have two ions, sodium and phosphate. So if we go to the periodic table, sodium has the symbol Na, and as we'll recall, we can use the periodic table to predict what the charge of the cation would be. So for these main group cations in group 1 and group 2, all of the group 1 cations are +1, so sodium forms a +1 cation. And then phosphate, we have to remember the name and formula for polyatomic ions as well. Phosphate is PO4 with a 3- charge, so remember that we have to keep that vocabulary straight. And so if we want to balance the charges here by doing sort of that trick, if you prefer, what we end up with is 3 sodiums, so the charge on phosphate becomes the subscript on sodium, and 1 phosphate, Na3PO4. So we need 3 sodium cations to balance the -3 anion and get a neutral ionic compound. So that's the formula for sodium phosphate. Now we're doing mole conversions that we're starting with mass. So if we have mass and we're asking you about moles, then we need to know the molar mass as part of that. So remember molar mass, which is sometimes abbreviated as MW for molecular weight. We take the sum of all of the individual atomic masses. So sometimes we'll give you molar mass, sometimes we won't. Here we didn't give it to you. So our molar mass, we have 3 sodiums, and we use the periodic table to figure out what those individual atomic masses are. So sodium is 22.99. We have phosphorus as part of the formula, which is 30.97. Oxygen, which is 16. So we have 3 sodiums that are 22.99. That's the contribution from sodium. We have 1 phosphorus, which has an atomic mass of 30.97 from the periodic table. And then we have 4 oxygens, which are 16 each, or 15.999 if you're really a stickler about decimal places. And what we end up with is 163.94 for the molar mass of sodium phosphate. Okay? So that's one of the first things we covered back in Chapter 5. We've been using it a lot, but figuring out the molar mass of a compound involves summing up the atomic masses of the elements. And then finally we're ready to do the conversion because we have that molar mass that we need. So we're looking, and when we're doing problems that involve conversions, as I always say, look at what it's asking you for. So it's looking for moles of sodium ions, moles of Na+, okay? And so we're starting with an amount of substance that's 65.65 grams of sodium phosphate, the whole thing, the first thing we'll do is convert into moles of sodium phosphate. So we use molar mass. So we want moles of sodium phosphate in the numerator, mass in the denominator. So this number goes in the denominator because that's the number of grams in 1 mole. So we can invert that to find out the number of moles per 163.94 grams. So grams cancel out. Now we have moles of sodium phosphate. But this is where a lot of people would stop and then end up getting the wrong answer, because especially if you don't write things out carefully, if you just do this conversion, you're finding the number of moles of sodium phosphate, but what we're looking for is moles of sodium ions. And so in this compound here, we see that there's a subscript of 3 next to sodium, as we determined at the beginning of the problem, which means that we have 3 moles of sodium plus for every 1 mole of sodium phosphate that we have. Okay? So if we're asking you about moles of individual ions or individual atoms in a formula, we have to account for how many of those are actually in the formula, not just do this simple mole conversion to start with. So writing out things carefully is always going to help you keep track of what you have. And so what we do then is when we multiply that across, we get 1.201. This I had set up as a numerical question, so we would just write the number 1.201 into Blackboard. Okay? But if you forgot this last step here, you would have gotten a number that was 4 times too small, and that would be, 3 times too small, and that would be an answer that very many people would likely pick, forgetting this last step here to account for how many sodium ions are in each formula unit of sodium phosphate. All right, questions on this one? All right, so then another type of problem that can come up dealing with mole conversions is taking mass percent and converting to empirical formula, or there's some other variations like combustion reaction, combustion analysis and things like that, where we're taking masses of elements, converting them into moles, and then finding the lowest ratio to get the empirical formula. So whenever we have a mass percent, so we have a compound here called catechol, which has carbon, hydrogen, and oxygen. We know the mass percent of each of these. In that situation, we assume that we have 100 grams of compound. And that means what we can do then is find the moles of each element where the mass of each element is going to be given by the percent. So if we have 100 grams of this compound, that means 65.4 grams are carbon, 5.49 grams is hydrogen, and 29.1 grams is oxygen. So for each element, we're going to convert the mass into moles. Because an empirical formula tells us the smallest whole number ratio of moles of each element, so we're going to take each element and figure out how many moles that corresponds to. So for the moles of carbon, we have 65.4 grams if we have 100 grams of compound, and then we're just going to use atomic masses to convert to moles. So the same step we started with last time, this time just a single element, so we only need the atomic mass, which for carbon is 12.01. Hydrogen we'll use later is 1.008, and we have oxygen again, which is 16. So we're going to use the 3 atomic masses to convert mass to mole. So we have 1 mole of carbon has a mass of 12.01 grams. So grams cancels out. That gives us moles of carbon is 5.45. And then for the other elements, we do the same thing. Moles of hydrogen. We have 5.49%, so that means in 100 grams of compound, we'd have 5.49 grams of hydrogen. The molar mass of hydrogen is very close to 1, so that number is going to end up being the same when we divide by the atomic mass, which is 1.008, for being real precise. So 1 mole of hydrogen has a mass of 1.008 grams, which means that we have 5.44 moles of hydrogen, very close to the same number. And then finally, the last one, oxygen. For the moles of oxygen, we have the last percentage here is 21.9, so there's 21.9 grams of oxygen, and the molar mass, atomic mass of oxygen is 16.00. So grams cancel, and we get 1.82 moles of oxygen. All right. So then when we end up dividing these, we have C, we have 5.45 moles. Hydrogen, we have 5.44. Oxygen, we have 1.82. So that's the mole ratio of the elements. But we want to express this in whole numbers for an empirical formula. So we do that by dividing by the smallest. These aren't anywhere close to whole numbers, so we don't want to do any rounding here. We divide by the smallest number, 1.82, 1.82, 1.82, which is the smallest of those 3 numbers. And we get a number that's very close to C3H3O. Okay? All right? So that's going to be choice A here for the correct empirical formula. We can eliminate a couple of these because this is not an empirical formula because it doesn't have the smallest ratio. 6, 6, and 2 can be reduced. This is not an empirical formula because it has a fractional subscript. So really there's only two choices we even have to consider, and the one that matches up is choice A. All right, any questions on that? Okay, let's move on then. All right, now we're dealing with balancing equations. So we have, barium phosphate reacting with sulfuric acid to form barium sulfate and phosphoric acid. What is the coefficient on sulfuric acid when the equation is balanced with the smallest whole number coefficients? So there's going to be problems where you might have to do this, balance an equation and give something about the coefficients, or sometimes we'll do stoichiometry problems where you have to produce the chemical equation as part of the problem. So this is going to be an important skill set for us either way. All right, so we have barium phosphate. We need to get the formulas for each of these compounds. So barium phosphate is going to be barium, and then we go to the periodic table. I should have given you the symbol for barium because it's beyond 36. So barium phosphate is Ba for barium. That was my mistake for not telling you that symbol. Ba should have been given to you because it's not one of the first 36. So barium is 2+, so it's in the second column. Phosphate is PO4 3-, so that means the formula of barium phosphate is going to be Ba3 and then phosphate taken twice, so we take the charges and cross them, make sure that the charges are balanced. That's our first reactant. Our second reactant is sulfuric acid. So we have SO4 2- is sulfate. That's the anion that it comes from. So that means sulfuric acid is going to be just 2 hydrogens to balance that charge, H2SO4. And then the products are going to be barium sulfate is our first product, which is barium 2+, and sulfate 2-, which is BaSO4. And then our coefficient, our last product is phosphoric acid, so H3PO4. So again, just a quick review of how to take names and convert them into formulas. We have to be able to do that for especially ionic compounds, and acids are going to come up a lot in this section of the course. All right, so these are the two reactants and the two products. So we arrange them on opposite sides of the arrow. Barium phosphate plus sulfuric acid. This is not the type of equation where you'd be able to easily predict the products. It's a weird acid-base reaction, but not one of the typical ones that we deal with. But we told you here that the products are barium sulfate and phosphoric acid. And then we just have to add coefficients to make sure that the elements on both sides are equal. So for ionic equations, especially that deal with ionic compounds and acids, I like to treat sort of each ion as its own sort of individual unit. So we have over here on the left side 3 bariums. So that means we need to have 3 over here. So we don't put subscripts, we put coefficients. We don't modify the formula. We just modify how many of them there are in the equation. So 3 there. Now by putting 3 there, we now have 3 SO4 2-, 3 sulfates. So if we have 3 sulfates on the right, we need to have 3 on the left. So that means we have to have a 3 there. And then finally, to balance everything else out, we have 2 phosphates over here, 2 PO4 3- for the barium phosphate, which means we have to make 2 phosphoric acids. And I think in this did I do that correctly? I think I did. So we have 3 bariums, 2 phosphates, 6 hydrogens, 3 times 2, 2 times 3, 3 sulfate, 3 sulfate. So everything is balanced out in this case. So now what we're looking for is the coefficient on sulfuric acid, which is this reactant here. So that's going to be 3, choice C. Okay? So balancing equations does require us in many cases to go from name to formula. Once you have the formulas of the reactants and products, it's just a matter of figuring out which set of coefficients will lead to having the same number of atoms on both sides. Very often there's more than one way to approach the problem. So the order that I went in is not necessarily the order you have to do it, but at the end you should double check to make sure that you have the same on each side. So questions on balancing equations, or this one in particular, or anything in general. All right. All right, next one is our first stoichiometry problem. And this is also going to require us to balance an equation, so we have to do that as well. So we have butane, which is, as you know, is found in lighters in many cases. So we have 3.25 grams of butane. We're burning it in the presence of 12.5 grams of oxygen to form carbon dioxide and water. We want to know what is the mass of CO2 that forms in grams, okay? So the first thing we have to do, we have masses of substances, and we're trying to find the mass of another substance, so we know it's stoichiometry, so we need a balanced equation. So for a combustion reaction, as we're telling you here, you have your reactant C4H10 in the presence of oxygen, so oxygen is our second reactant, and we form carbon dioxide and water as the two products. So we've talked about combustion in a couple of contexts, and so whenever you burn something, as for example what happened in Deer Park earlier this week, whenever something burns, you typically make CO2 and water as your primary products if it's a perfect combustion reaction. All right, so that's the chemical equation to start with. We have to balance it, so we have 4 carbons on the left, so we put a 4 in front of CO2. We have 10 hydrogens here, so we have to put a 5 in front of water to make sure there's 10 hydrogens on the product side. And then we balance oxygen last because it appears twice on the product side. So now we have 8 plus 5 is 13 oxygens, 4 times 2 from CO2, 5 times 1 from water. 13 oxygens on the right, we need 13 on the left, so we can write that as 13 over 2. If fractional coefficients bother you, which they bother me a little bit at least, so we'll double everything to get rid of them. So if you have something over 2, we can double every single coefficient to get rid of that. Remember, we have to do that for all of them, not just the one that's a fraction. So we double every coefficient to keep everything balanced. We get 2 C4H10 plus 13 O2s goes to 8 CO2 and 10 water. So this is the fully balanced equation with whole numbers. So in this problem, then, we have to look when we're doing stoichiometry and figure out, do we need to determine what the limiting reactant is or not? And so what do we have to do here? Yes or no, determining a limiting reactant? I heard a no. I heard a couple more than one no. Anybody else? Anybody care to disagree? Okay, so now we're all starting to come around to the idea that in this problem we told you the masses of both reactants. We told you that you have 3.25 grams of butane. We told you that you have 12.5 grams of oxygen. So because we know the mass of two reactants, more than one, we need to figure out which one of those is the limiting reactant first. All right, so for each reactant, we're going to find the moles. So for C4H10, we gave you the molar mass as 58.14. We convert the mass into moles first, 3.25 grams. And we use the molar mass, like we've been doing a few times already, to convert that into moles of C4H10. So what I got was 0.0559 moles. And then to determine if it's limiting reaction, we also have to take the ratio. So we divide the number of moles, which is 0.0559. We divide that by the coefficient. So if we're using the bottom equation here that's balanced with whole numbers, the coefficient for C4H10 is a 2. So when we divide that, we get 0.0279. That's our stoichiometric ratio. This is what we're going to use to figure out if it's the limiting reactant or not. We do the same thing for our other reactant O2. We find moles first, so we have 12.5 grams of oxygen. We convert to moles using the molar mass. I didn't give that to you, but oxygen has an atomic mass of 16, so the molar mass of dioxygen O2 is 32. So grams into moles gives us 0.391. Now that looks like a much bigger number. It is. We have a lot more moles of oxygen than butane. But remember, to figure out if something is limiting reactant, we have to take the number of moles and divide it by the coefficient. So the stoichiometric ratio for O2 is going to be that number, 0.391, divided by the coefficient, which if we're using the bottom equation is 13. And when we divide that, we get R equals 0.03. So it still is a little bit bigger, but not much bigger than the first one. So remember, the one that has the smallest R, the smallest stoichiometric ratio, is going to be the limiting reactant. So that's going to be butane C4H10. Okay, so the numbers aren't that much different, but this one's a little bit smaller, so that makes that the limiting reactant. So now that we know what the limiting reactant is, we can use that amount, the molar amount, to figure out how much product forms. So what we're looking for here is mass of CO2 that forms. So we start with the moles of limiting reactant. We could also start with mass, but we already converted it to moles, which is the first step anyway. So we'll start with moles of limiting reactant, C4H10. Once we have moles of limiting reactant, we use coefficients in the balanced equation to relate that to the moles of product that form. So we're looking for CO2, so we know we want C4H10 to cancel and convert into moles of CO2, the product that we're looking for. We have a coefficient of 8 for CO2, a coefficient of 2 for C4H10, and so that's how many moles of CO2. And then the last step we said was to find the mass of CO2. To save some time, I should have also given you the molar mass here, which is 44.02. I guess 0.1, sorry. 0.1 grams of CO2 per 1 mole. So moles in the denominator cancels out. We convert to grams of that product by multiplying by its molar mass. And what we end up with is 9.84 grams of CO2. I think this one is also a numerical question, so we would just enter in 9.84 as our answer in the blackboard. Okay, so stoichiometry involves this bottom type of conversion here, mole ratios, very often molar mass is involved as well. But if we have amounts of 2 or more reactants, we have to take the time to figure out which one is the limiting reactant first before we just start calculating willy-nilly. All right, questions on this one? All right, we're going to see some more stoichiometry, so we're not done with this yet. All right, number 11 is another type of stoichiometry problem. Here we gave you the balanced equation, so that'll save us a little bit of time. So we have gold 3 chloride. We're looking for the amount of that's formed, the theoretical yield, which means the amount that could form. If we have 29.6 grams of gold, we have 50 milliliters of 4 molar HOCl, this reactant here, and excess HCl. So we want to know how much of this product can form here. So we have 3 reactants in this case that we have to worry about. So we have to figure out which one of those is limiting reactant if it's not immediately obvious from the problem. So in this problem, we're told that we have excess HCl, so we already know that that's excess. But we also are starting with 29.6 grams of gold, so we know the amount for that. And we also know that we have 50 milliliters of HOCl solution, so we have 50.0 milliliters. This problem sort of combines aspects of chapter 5 and 6 with stoichiometry and aqueous solutions. So because we know the amounts of 2 reactants, we again have to figure out which one the limiting reactant is. This time the 2 amounts are in different units. One of them is a mass, one of them is volume of an aqueous solution. But because we know how much of each reactant we have to figure out the limiting reactant before we start the problem. So we're going to do that same set of steps as the last problem. We're going to find the moles of each reactant. So starting with gold, we have just a mass to mole calculation for gold. We have 29.6 grams of gold, and we use the atomic mass, which is not given to us here, but it's on the periodic table. So gold is an element, so we just find the atomic mass on the periodic table. 1 mole of gold has an atomic mass of 196.97. So that converts us into moles of gold, 0.15. And the stoichiometric ratio then is that number divided by the coefficient. The coefficient in the balanced equation is 2, so it's going to be 0.075. So the stoichiometric ratio for gold is 0.075. We do the same thing for the other reactant that we know the quantity of, which is HOCl. That would be hypochlorous acid. So the moles of HOCl, in this case we don't have a mass to start with, we have a volume and a molarity. So this sort of jumps us forward into some things we learned in chapter 6, where if you have volume and molarity, remember that molarity is moles per liter, so we can use that as a conversion factor to also find the number of moles of substance in a chemical reaction. So we have 50 milliliters of a solution, HOCl aqueous, and then we use this molarity as a conversion factor. So 4.00 capital M means we have 4 moles of the solute HOCl for every 1,000 milliliters, or 1 liter is the standard definition of the solution. All right, but this is a little bit of a shortcut that I use. So per 1,000 milliliters of solution, we have 4 moles. So milliliters cancel, and that gets us into moles. So this is also just a one-step calculation to get number of moles, but it's a little bit different concept now using volume and molarity. So you have 0.2 moles of HOCl, but we have to find the stoichiometric ratio by dividing by the coefficient. So the number is 0.2. We divide by the coefficient here, which is 3, and that gets us to 0.067. So this number is smaller, which makes HOCl the limiting reactant. So again, we compare the two stoichiometric ratios to figure out what the limiting reactant is. So even though we have more moles of HOCl, the ratio is smaller, so that makes it limiting in this case. So now that we have moles of limiting reactant, we can look at what the question is asking us for, and it's asking us for the theoretical yield of gold chloride. We didn't specify a unit for that, so if we don't specify, you should assume that it's grams, although we likely would specify in the test. So we're looking for the mass of gold chloride that can form. That's our theoretical yield that we would calculate using stoichiometry. We start with moles of limiting reactant, which is HOCl. And just like in the last problem, once we have moles of limiting reactant, we use mole ratios to figure out how many moles of that product can form. So we want moles of HOCl to cancel, and moles of gold chloride in the numerator. So we have a coefficient of 2 in front of gold chloride, so we put a 2 there. We have a coefficient of 3 in front of HOCl, so we get a 3 there. And then once we have moles of our product, we can find mass by using its molar mass, 303.32. So we have 303.32 grams of gold chloride per 1 mole. So once we have moles, we multiply it by molar mass to get back into grams. And working all that out, we get 40.4 grams. I think I specified 2 decimal points, and I don't know what the second one would be. I don't know if it's, is it 0? 44, okay. So really whatever you have in the second decimal place is not going to cause you to get that wrong anyway. But to follow the directions closely, we get that much product formed, and then would enter in that as our answer. Or something very close to that would still get counted right. Remember, on numerical questions, we usually give you a 1 to 2% sort of window that you can put your answer into. So on this question, even if you were off by 0.3 or so, even if you had a 40.7, you'd still probably get it counted right because that's within 1% of the answer. So there's a little bit of leeway in case you're rounding. But as sort of a word of caution and as a good practice, don't do any rounding until the end. So at least keep 3 or so decimals, 3 or so significant figures as you work through all the intermediate steps, and don't do any rounding until the very end to make sure you don't lop off too many decimals and get your answer wrong that way. Okay, questions on this? All right, number 12. So now we're dealing with more conceptual type questions for aqueous solutions. So we have a list of compounds here. We want to know which of the following would not conduct electricity at all. All right, so remember what we have is, when we're talking about electrical conductivity of solutions, we have 2 major categories of compounds when we dissolve them in water, whether they're that determine whether they conduct electricity or not, and then we have one subcategory within there. So if we have electrolytes and non-electrolytes, so we have electrolyte solutions will conduct electricity, and within that we have strong and weak. So strong electrolyte, weak electrolyte is sort of one major category. And both of these solutions would conduct electricity. The only difference is how well they conduct electricity. So as the name implies, a strong electrolyte would conduct electricity better than a weak electrolyte. Now in terms of identifying whether a solution is a strong or weak or non-electrolyte, that comes into play with what kind of compound it is. We'll get there in a second. The other major type is a non-electrolyte solution, which doesn't conduct electricity at all. So these, when they're dissolved in water, do not conduct electricity. And then in terms of what kind of compounds fall into these categories, strong electrolytes are going to be ionic compounds and strong acids. So these are ones that completely break up into ions when we dissolve them in water. It, of course, has to be a soluble ionic compound. If it's not soluble, it won't dissolve and it won't conduct. But any ionic compound that dissolves in water will become a strong electrolyte solution and have ions that can conduct electricity. Weak electrolyte solutions, the two categories that fall into these are weak acids and bases. So these are two technically covalent compounds. When they dissolve in water, you get some amount of ions formed, not a lot, so that's why they're considered weak electrolytes. Most of the molecules stay intact, but you get some ionization. And then finally, the non-electrolyte solutions are typically covalent compounds that are not acids or bases. So things like sugars, alcohols, which are covalent compounds. They have only nonmetals in the formula, but they're not acids or bases, so they don't ionize at all when you dissolve them in water. The molecules stay completely intact. So that's kind of the concept we're dealing with here. So then for all these answer choices, we need to identify what kind of compound it is and then whether that makes it a strong, weak, or non-electrolyte. Here we're looking for the one that doesn't conduct, so we're looking for the one that would be a non-electrolyte solution. So HNO3, what kind of compound is this? It's a strong acid, so that makes it a strong electrolyte solution when we dissolve it. So that's not going to be our answer choice because we're looking for the one that's a non-electrolyte. CaCl2, this is what kind of compound? Calcium chloride. Ionic compound, it dissolves in water, which makes it a strong electrolyte. So this is a soluble ionic compound, making it also a strong electrolyte. All right, and then the one that we come across a lot in this context, we have CH3CH2OH. We don't expect you to know the name of this, but this is called ethanol. This is a type of anything that has OH at the end is an alcohol, which makes it a non-electrolyte. So this is going to be a covalent compound, but not an acid or a base. So this is going to be the one that we think we're going to pick. As a slight distinction, there's also acetic acid, which looks very similar. This also ends in OH, but if it ends in OOH, that designates it as what's called a carboxylic acid, which anyway, this makes this a weak acid. So they don't look that different in terms of their formula, but acetic acid, which we know the name of and has the name acid in the formula, is a weak acid. Other things that end in OH, alcohols in particular, are not acids at all. So you'll learn the chemical differences for that later on, but just to keep those straight in our own heads, this one is a non-acid, this one is a weak acid. So this one is a covalent compound. Here we have a soluble ionic compound, so that's going to be a strong electrolyte. H3PO4 is another weak acid. So this would be a weak electrolyte, but it would at least conduct a little bit of electricity. The only one that does not conduct electricity at all is choice C, which is our alcohol non-electrolyte solution. Yes?
How do you know what ionic compounds are
Solubility rules. So we will cover that a little bit later on, but we had sort of a list of rules that dictates, based on the cations and anions in the formula, whether the compound will or will not dissolve. So for the ones that we had here, calcium chloride, most chloride salts are soluble unless it's lead or silver being the two most popular exceptions, and copper and mercury being less common ones. So calcium chloride would be soluble. And then for KOH, anything with potassium in the formula is soluble. So whether it's whatever anion is paired with, you would expect any potassium salt to be soluble. So these two are both soluble because they do have the right anion and cation combination to make them soluble. We will cover solubility rules a little bit later on in this review. Not in full detail, but we'll use them a few times to make some predictions. All right, other questions? Yep. Well, a strong base is a strong electrolyte, but a strong base is also an ionic compound. So all the strong bases that we have are hydroxide ionic compounds. So it would you could still say that a strong base is a strong electrolyte, but it's not a separate category really because it's also an ionic compound. That's a good question. Yeah? How do we know if it's an acid or a base? So the acids you should be familiar with because we talked about the nomenclature of acids, and so the acids usually start again with hydrogen at the front, pair with some anion, and we learned how to name those back in chapter 3. The common strong acids are HCl, HBr, HI, HNO3. In terms of what the bases are, the vast majority of bases have hydroxide in the formula. So they're ionic compounds that have OH minus as the anion. So just about every base you'll see has that. The only weak base that you'll need to worry about would be NH3 ammonia. So that's the only weak base that we'll really deal with in this class. Every other base would have OH minus directly in the formula for you and be able to identify it that way. Other questions? All right, on to number 13. All right, so we did this one is another sort of mole conversion, but this time dealing with an aqueous solution. So it has some similarities to one of the earlier problems we did. So here we have a solution where we take 25.65 grams of calcium perchlorate. We dissolve it in 1.23 liters of solution, and we want to know what is the concentration of perchlorate ions. So for this problem, we need a few things here. First of all, we need the formula of the compound because, again, we're doing mass to mole conversions. We did give you the molar mass, but we still need the formula because we're looking for the number of perchlorate ions that are in there. So that's going to be related, as we'll see here in a second. So calcium perchlorate, we have calcium and we have perchlorate, which is ClO4 minus. We go to the periodic table. Calcium is in group 2, so we predict that the charge of the cation is +2. So the formula for calcium perchlorate is going to be Ca with 2 perchlorates, calcium with 2 perchlorates to balance the charge. So that's the formula of the compound. And then what we're looking for in this problem is the concentration of perchlorate ions in molar. This mic's a little bit hot. Let me turn it down here. So that hopefully is better. All right, so everybody can still hear me? Even the back dwellers, okay? All right, good. So the formula is calcium perchlorate is that. And then the molarity, what we're looking for the concentration in molarity units of ClO4 minus individually. We're looking for just the perchlorate ions, not the whole thing. So what we need to be able to solve this is the moles of perchlorate, moles of ClO4 minus, and the liters of solution that we made. Remember, molarity is always defined as moles per liter, so in this case we need to make sure we use the correct unit in the denominator. So in this problem here, we see that we're told directly that the volume of the solution is 1.23 liters, so we have that number already. So we'll put that in the denominator. But then we need to find the moles of perchlorate, which we don't have directly. So this is again going to be just a mole conversion that we're going to set up the same way we've done before. Moles of perchlorate, we have 25.65 grams of the ionic compound dissolved. And then we convert that into moles using its molar mass. So 1 mole of calcium perchlorate has a mass of 238.98 grams. So that gets us 2 moles of calcium perchlorate, but the step that I want to emphasize yet again that we had earlier that many of you forget is that we are only looking in this case for the concentration of perchlorate ions. So if we're dealing with concentrations of individual ions or the total concentration of ions, if that was the case, we need to think about how many of those ions are in the formula. So this is calcium with 2 perchlorates, so we know that there's going to be 2 moles of ClO4 minus for every 1 mole of calcium perchlorate that we dissolve. Okay, so this last step here, relatively simple, but is one that's easy to forget, especially if you're not running things out in full detail. So then what we end up with is 0.2147 moles of ClO4 minus. So we put that number up here, 0.2147 moles divided by 1.23 liters. That gives us a concentration in molarity of 0.175 molar, which we would enter in just the number in a blackboard as instructed. Okay? All right, so that's how we calculate molarity. The only thing that's a little bit outside the box here is remembering that if we're doing it for individual ions, we have to account for the formula of the compound and figure out how many ions there actually are. All right, questions? All right, let's keep it going then. All right, in number 14, we have 125 milliliters of water added to 225 milliliters of 0.254 molar NaCl. What is the final concentration in molarity? So here we should recognize immediately this is a dilution problem. We just have one substance. We're not reacting the substance with anything else. We're just adding water to change the volume and the molarity. So anytime you have that situation, we're talking about dilution. And so the formula that we should zone in on is M1V1. The product of the initial molarity and the initial volume is equal to M2V2. And so then what we're solving for here is the final concentration, which I'll call M2, but whatever you label as M1 and M2 is sort of arbitrary. So M2 is going to be given by the product of M1V1 divided by the final volume V2. All right. Now most of these are given to us in the problem. So the initial molarity M1 is 0.254. So we have 0.254 molar for M1. The initial volume is 225 milliliters. The part that we have to keep in mind here, though, is that V2 is not the volume of water that we add. V2 is the total solution volume after we do the dilution. So we're telling here that we assume the volumes are additive, which is a not perfect but pretty good approximation. So that means our final volume V2 is going to be the volume that we started with, 225 milliliters, plus the amount of water that we add, which is 125. All right, V2 is not the amount of water we add by itself. It's the final volume of the solution after dilution. So our final volume V2 is going to be 350 milliliters. So that's what we'll put down here. For this equation, because it's a ratio of two volumes, we don't necessarily have to convert into liters. You would still get the right answer if you did, but we have milliliters for both of these, so milliliters cancels out. And when we multiply and divide, what we end up with is 0.163 molar. The number would be what we would put into Blackboard just to keep emphasizing that point. Although I think most of you get that part okay. All right, so again, M1V1 equals M2V2, relatively simple. You have to make sure in this case that we didn't gloss through things too quickly and realize that our final volume is actually a sum of the volume we started with plus the volume of water that we added. All right, questions? Okay. All right, so now we're dealing with a few questions dealing with aqueous chemical reactions. And so in this first one here, we want to know which of the following mixtures will not form a precipitate. So we're giving you combinations of two ionic compounds. I think all these are ionic compounds in this case. You'd have to be able to predict the products and then use solubility rules, which we referred to before, to decide which of the products is or is not soluble. So remember, if you're looking for the one that will not form a precipitate, you're looking for the one where both products end up being soluble ionic compounds. All right, so for choice A here, whenever we're dealing with precipitation, remember that the approach we take is we look at the two reactant formulas and we swap the cations and the anions. So the cation from the first ionic compound will get paired up with the anion from the second in the product. So the first product in choice A is going to be potassium paired with nitrate. So that's going to be KNO3. And then the second product is going to be silver Ag plus paired with chloride Cl minus. We don't even have to balance the equations here. All you really need to know for this problem is what are the identities of the products and whether any of them are insoluble. So we're looking for ones that are insoluble here. So the first product here has potassium and nitrate in it. And from our solubility rules, these are both ions that would always be soluble. So whatever compounds are in potassium, NO3 minus, those are two ions that are always soluble, so that one's not going to precipitate. But AgCl, most silver compounds are insoluble unless they're with nitrate or a couple other of special anions like perchlorate and acetate. So this is going to be insoluble. So I'm going to circle the insoluble products. So we can eliminate choice A because we're looking for one that will not form a precipitate. In choice A, we would expect silver chloride AgCl to precipitate from solution. All right, choice B, we do the same thing. We have cation from the first reactant is ammonium, NH4+. Plus. It's going to pair with perchlorate, so NH4ClO4 is ammonium perchlorate, +1 and -1 charges. Formulas are important, although for this one, as long as you know the solubility rules, you'll be okay. I think ammonium perchlorate is explosive, but at least if it's dissolved in water, it'll be okay. And then the second product from this is going to be, we have our cation from the second is lead 2+, the anion from the first is SO4 2-, so we're going to form lead sulfate. And then lead is one of those cations like silver where most compounds with lead are insoluble. So again, unless lead is paired with nitrate perchlorate acetate is sort of the three common exceptions, lead compounds are typically insoluble. So this would also form a precipitate, so I'll circle that and X out that answer choice because that would also give an insoluble product. Choice C, cation from the first reactant is sodium, anion from the second is chloride, so we form NaCl as a product. And then the cation from the second reactant is barium, and the anion from the first is carbonate. So we have barium carbonate as our second product. And in these ones, again, all sodium compounds, group 1 cations are soluble. We should be fairly familiar with sodium chloride as being soluble because we've dealt with salt water all the time, living on the Gulf. And then finally, barium carbonate. Carbonate is an anion that is almost always insoluble unless it's paired with lithium, sodium, potassium, so on, that group 1. So barium carbonate is an insoluble, so that would form a precipitate, so that's not our answer choice. Choice D, sodium hydroxide, iron chloride. So we get sodium paired with chloride again, so sodium chloride would be one of the products for this one as well. And then we get iron paired with hydroxide, which is iron 3 plus in this case because it's 3 Cl minuses, that's 3 plus charge, so it's going to be FeOH3. Hydroxide is another anion like phosphate and carbonate where it's usually insoluble unless it's with mostly the group 1 cations, a couple exceptions from group 2. So all of our transition metal hydroxides, though, especially, we would expect to be insoluble. So this is another insoluble, so that would precipitate. So by elimination, we should hope that choice E is the correct answer that does not form a precipitate. Let's see if that's true. So we have calcium nitrate and ammonium chloride. So calcium would get paired with chloride to make CaCl2, calcium 2 plus Cl minus. And then our second product is going to be ammonium nitrate, NH4NO3. The obvious one of these two is ammonium nitrate. Both the cation and the anion are always soluble, so ammonium nitrate would remain soluble. And then calcium chloride, most chloride salts are soluble, except for a few of the sort of late transition metal exceptions like silver, lead, mercury, copper. So all of the group 1 and group 2 halides with calcium and sodium, we would expect those to be soluble. So both of these are soluble, and this is going to be then the answer that we pick. So if you mixed solutions of these two compounds together in choice E, you would not get anything precipitating. Everything would just stay dissolved because both of the possible products that form are soluble based on solubility rules. All right, so I know solubility rules are a little bit of a pain in the neck. So make sure you learn them very well. Look for the obvious ones first, the sort of ones that are always soluble. Especially, you can usually pick those out pretty quickly and at least eliminate some answers that way. But there are, a fair number of rules that you need to be familiar with to be able to handle these problems effectively. All right, questions? Yep. Well, there are no metals that are always insoluble. So the ones that are sort of the closest to that would be like silver plus and lead 2 plus. These are usually insoluble. So you would predict that based on the anion they're paired with. So if these are paired with nitrate, perchlorate, or acetate, which are sort of our 3 special anions, those would still be soluble. If they're paired with any other anion, they would be insoluble. So it depends on what the pairing is. And so in that first category that I gave you in lecture when I introduced solubility rules, there are a number of cations and a few anions where if they have even just one of those in the formula, they will be soluble. It doesn't matter what the other thing is. So in that case, you would always predict it's soluble, and then from there, there's a lot, more exceptions you have to deal with for the other rules. But those are the ones that you should zero in on first, because then you know that compound is soluble, no matter what the other cation or anion is with it. Okay. Anything else? Yep. So it's FeOH3 because this is a transition metal, so the charge is variable. So you have to look at the formula to figure out what the charge of the cation is. So if we have 3 chlorides, remember that chloride is always -1. So if you have 3 -1s, that means the metal must be +3 to balance the charge. So if the metal is +3 and you're going to now pair it with OH, which is also -1, that means you need one metal with 3 hydroxides to still balance the charge. So when we do precipitation, we don't change the charge on any of the anions. We're just swapping them with each other. Redox equations is where you would see potentially the charges of ions changing. But those ones, we don't have to predict the products. We just have to balance them. Okay? Questions? All right, we're in the home stretch. So number 16. All right, this is a similar type of question. We're dealing with solutions of ionic compounds and predicting spectator ions. So we have a reaction between barium nitrate and sodium phosphate, and we want to know if there are any spectator ions or if all of them potentially are spectator ions. So in this situation, we again need to write out the formulas of the two reactants, predict the two products, decide whether or not they're soluble or insoluble. All right, so barium nitrate is going to be barium 2 plus. I should have again given you, well, I gave that to you here in the answer choices. So you know that barium is Ba and it's 2 plus, nitrate is NO3 minus. So sometimes you can look at the answer choices for clues. So if you're stuck on, oh, I don't know what the symbol for barium is, oh, I don't know if it's +1 or +2. Well, if you look at the answer choices, all the answer choices with barium are +2, so that's likely going to be the charge for barium. So we have barium 2 plus, NO3 minus, so the first reactant is barium with 2 nitrates. And we're always starting with 2 aqueous solutions, so we don't have to worry about the solubility rules of our reactants. We just have to worry about solubility rules for the products that form. Sodium phosphate is going to be Na3PO4, sodium plus with PO4 3 minus. And then the two products are going to be where we swap the cations and anions. So barium is going to get paired with phosphate. So we have barium 2 plus paired with PO4 3 minus. So when we cross the charges and balance them, we get Ba3PO4 2. So a little bit complicated of a formula there. I think we might have had this in an earlier problem too. And then the other product is going to be sodium paired with nitrate, which is just NaNO3. All right, so those are reactants and products. For the products, we have to think of solubility rules. I jumped the gun and let the cat out of the bag early, but if we think about these two products here, phosphate is one of the anions that is usually insoluble unless it's with group 1, so unless it's with sodium, potassium, lithium, and so on, or ammonium. So this is going to be insoluble, so that's going to be our product that forms. Sodium nitrate, dead giveaway, both the cation and the anion are always soluble, so that will remain in solution. So if we're asking for spectator ions, there's a few ways to go about this. I guess it's helpful to balance the equation 2 first. So we have 3 bariums on the right, so we need a 3 there. If we have now 6 nitrates, 3 times 2, we need a 6 there. And if we have 2 phosphates, we need a 2 there. So again, make sure we put coefficients in. These are about as big as the coefficients we'll get for ionic equations, 3, 2, 1, and 6. Everything is balanced. I'm not going to go through that in detail. If we want to then write out the full ionic equation, to figure out spectator ions, we look for the ions that appear on both sides. The shortcut way to do that is to look at the ions that are aqueous on both sides as well. So that's kind of what we're looking for here, is the ions that remain dissolved in solution both as reactants and as products. So we see, if we want to do it sort of the short way, that we have nitrate is aqueous here, nitrate is aqueous there, so that's one of our spectator ions. And then sodium is still part of an aqueous compound on the right side. Sodium is also part of an aqueous soluble compound on the right and left. So those are going to be our spectator ions, are going to be sodium plus and NO3 minus. We want to do it sort of that shortcut way. The long way of doing this, the more thorough way, is to break this up into the ionic equation and then figure out which ions appear on both sides. Those are going to be your spectators. So if we take this and separate all of the aqueous compounds into ions, we get, going to be a lot to write here. So we get 3 barium 2 pluses. We get 3 times 2, which is 6 NO3 minus. We get 6 Na plus. 2 times 3 is 6. 2 phosphates. That 2 modifies the whole compound. So we get 2 PO4 3 minuses. Those should also both be aqueous. And then the product side, we don't separate compounds that are insoluble. So the one that's marked with a little S here is insoluble. We keep that together as barium phosphate. And then we have 6 Na plus, 6 NO3 minus. So these full ionic equations are kind of unwieldy in some sense. And then to find spectator ions, we look for the ones, this is our total ionic equation. Spectator ions are the ones that appear on both sides. So we have 6 Na plus there, 6 Na plus there, 6 NO3 minus there, 6 NO3 minus there. So that means, again, Na plus, NO3 minus are spectators. The net ionic equation, which we don't ask you for here, but if you wanted to write it, would be 3 barium 2 plus, basically whatever's left over after we get rid of spectators. 3 barium pluses, 2 phosphates, forming barium phosphate. So we could also have skipped to the net ionic equation. The net ionic equation is basically the combination of the ions that form the insoluble product, we write that out first, and the ions that are not involved in forming the insoluble product, sodium and nitrate, would be your spectators. So a lot of different ways of sort of thinking about this, but spectator ions are the ones that are dissolved in solution on both reactant and product side. They're not involved in forming the precipitate when you have a precipitation reaction or an acid-base reaction. Okay, questions on this one? All right, so that's that one, and then, all right, last one is sort of that deals with stoichiometry, is going to be a titration type problem. So we're doing an acid-base titration here. We have a 2.34 gram sample of an unknown diprotic acid with 2 acidic protons. We're going to neutralize that with 0.375 molar NaOH solution. It takes 40.9 milliliters of the solution to neutralize the acid. So what is the molar mass of the unknown acid? So this is a titration problem. We're taking 2 solutions and mixing them together. We know the volume and molarity of one of the solutions. The other component we don't know something about. We're trying to find it out. So it's helpful to write what we're looking for, because again, that zeroes us in on what information we need. So we're looking for the molar mass of our unknown diprotic acid. So if it has 2 acidic protons, I'm going to abbreviate the formula. We don't know what it is. I'm going to abbreviate it as H2X to remind myself that this acid has 2 acidic hydrogens in it, 2 acidic protons. So the molar mass of H2X, that's going to be important later on, not for now, but the molar mass is always defined as the grams, the number of grams of the substance, divided by the number of moles. So anytime we're looking for unknown molar mass, which comes up in these types of problems, or maybe some other ones we'll see on this test as well, you look for the mass of the substance, you look for the number of moles, and you divide the two. All right? So in this problem here, the mass is given to us directly, so that's going to be 2.34 grams. We already know the mass of our unknown. But we have to find the number of moles to be able to solve this question. And so now, whenever we're looking for number of moles in a titration problem, we're going to use, again, the molarity and volume of the other solution to help us find the moles of whatever our unknown solution is. So we have to know a little bit about how these two react with each other. So this is an acid-base reaction. So we have our acid H2X, and the base we're neutralizing it with is NaOH. And so what's important here is the ratio that these two react in. So for titration problems, you really just care about the two reactants that you're combining, and you need to know what mole ratio those two react with each other in. So if our if our acid has 2 H pluses, remember that each H plus has to combine with 1 OH minus. So if we have 2 H pluses, we need 2 OH minuses. Our base only has 1 in the formula, so that means it needs to get a coefficient of 2 to make sure we have 2 of each. All right, so that's the important part, is that our acid and base in this case will react in a 1-to-2 ratio because our acid has 2 H pluses, which means it will combine with 2 OH minuses to neutralize. Now, if we wanted the products here, which we don't really care about for this problem, but we would form as a result 2 molecules of water, because each H plus and OH minus make 1 molecule of water, and then the other product is going to be just the cation that's left over, sodium, paired with the anion X2 minus to make an ionic compound NH2X, which we don't care about in this case or don't know the identity of either. So what we really need, though, is the reactants ratio, so we can find then the moles of the acid that are involved in this titration. So the moles of H2X are going to be, we start with the volume of the solution where we know the molarity, so we have 40.9 milliliters of our NaOH solution. And as we've seen a couple times already, if we know the volume of solution and we know the molarity, we can figure out number of moles by using molarity as a conversion factor. So that molarity, capital M, tells us that in 1,000 milliliters of solution, which we'll put in the bottom here, we have 0.375 moles, 3.375 moles per 1 liter or per 1,000 milliliters as a shortcut. So milliliters cancel out, and now we have moles of NaOH. What we're looking for, though, is moles of the acid, and that's where we have to use mole ratios now. So this is now stoichiometry, where we want moles of NaOH to cancel out, so we put that in the bottom, moles of H2X in the top, and we see that the coefficient for H2X is 1, the coefficient for NaOH is 2, so it's a 1-to-2 mole ratio, and that gets us into moles of acid, which is what we're looking for. So when we multiply that across, we get 0.00767 moles of the unknown acid H2X. We put that into the denominator here. I'll just put it in as moles. So grams per mole. We divide the two, we get 305.1. 1 decimal place, no units, so the units would be grams per mole. We would enter in the number 305.1. All right, so in a titration problem, there's a few things you could be asked to find. You could be asked to find the molarity of a solution, or an unknown molar mass, or maybe the volume of the other solution that's required to neutralize it. A lot of different variations depending on what information we give you. But again, it's using molarities and volumes as a way of finding moles, and then mole ratios to relate one substance to another. So titrations are really just a fancy way of saying solution stoichiometry. It's just different information that you need to get depending on what we're asking you for. All right, questions on this? All right, and then the last three problems we're going to go through, which is going to be indicative of how the exam is going to be, is going to have three questions dealing with oxidation reduction. So either oxidation numbers or balancing redox equations, which we covered fairly recently, so definitely need to make sure we practice on that. So the first question here is just asking about oxidation numbers. Which of the following is the oxidation number for nitrogen correct? So we have all these different compounds with potential oxidation numbers. So we have to look through these answer choices and see which one is the oxidation number correct. So in choice A here we have HNO3. We want to find the oxidation number for nitrogen. So nitrogen is one of those elements that's pretty variable in terms of oxidation number, so we have to sort of go through the rest of what it's paired with and then kind of get nitrogen last. So the way we do that is we look at, in covalent compounds, hydrogen and oxygen are pretty constant. So they're going to be +1 for hydrogen and -2 for oxygen. The sum of the oxidation numbers always has to equal the charge of the compound or the ion. HNO3 is a neutral compound, so that means the sum of the oxidation numbers has to be 0. So if we have 3 -2s and a +1, that's -5. That means we need a +5 on nitrogen so that they all add up to 0. So for HNO3, the oxidation number on nitrogen would be +5. That's incorrect here. It says +4 for choice A, so that's wrong. We're looking for the one that is correct. For choice B, we have NO2. This one's a little bit more straightforward now because we only have 2 elements. And as I said, in covalent compounds with very few exceptions, or any compound with very few exceptions, oxygen is going to be -2 for its oxidation number. So if we have 2 -2s, what does nitrogen have to be to add up to 0? +4. So we have 2 -2s, we have a +4, they add to 0. That is also wrong then. That should be +4. In choice C, we have NCl3. So chlorine, if it's the outer atom in a formula, if it's not the central atom, it's going to always be -1, just like it is in ionic compounds. So chlorine is typically -1 unless it's the central atom of like a polyatomic ion like perchlorate or something. So it's -1 if it's on the outside. 3 -1s leaves nitrogen as +3 so that they add up to 0. So that one is wrong also. And then finally for choice D, we have an element by itself, N2, no charge. So what's the oxidation number? Someone said it already. 0. All right, so that's not -1, 0 if it's a neutral element with nothing else in the formula. So all of these are wrong, which means you have to make the psychologically difficult decision to pick none of the above as the answer. All right, so that would be the answer for this one, is none of the above. All of those have the wrong oxidation number for nitrogen. All right, so that gives you sort of some practice in finding oxidation numbers. As I said, hydrogen and oxygen are two that show up a lot, which you want to look at first because they're typically always +1 and -2. And then from there, there's a lot more variation. For ionic compounds, if you know the charge of the metal, which you can find from the formula, that charge is also the oxidation number. So there's some that are fairly easy to deal with. Others, like nitrogen especially, where you have to kind of use that, sort of save that for last and base that on what else is in the formula. All right, questions on how to find oxidation number. All right, the last two then, which are a lot of fun, are going to be balancing redox equations. So in these types of problems, there were a couple on the homework that we went a little bit beyond what you should have to do. So we'll always give you all of the reactants and products, so you don't have to worry about, oh, is there H plus or water. If it's there, it'll be in the equation, and you just have to give the coefficients and answer some question about those coefficients. And so we always would start with that. Now for these types of problems here, you again need to be able to do oxidation numbers. So we're looking for the sum of the coefficients in this equation here. So it's very difficult to do these by inspection because in a lot of redox equations you have not only to worry about the number of elements that you have on each side, but like we do for any chemical equation, but you have charges on each side too, and the charges have to balance as well. So it's very hard to know just by putting in numbers randomly and sort of adjusting them to make sure that you keep both elements and charges balanced. That's almost impossible to do by inspection, so we want to use the oxidation number approach to do this. So I will rewrite everything down here so that we can make sure that we have enough room to write all that information. So we have H plus, we have MnO4 minus, we have NO as reactants, and then on the product side we have Mn2 plus, NO2, and water. All right, so we write out reactants and products, and for each reactant and product we need to figure out what the oxidation numbers are of all the elements. So same approach that we used in the last problem. Ones that are simple for us are going to be ones that are ions by themselves, monoatomic ions. So if you have H plus by itself, the oxidation number is just the charge, which is +1. Here we have Mn2 plus by itself. The oxidation number of any ion by itself is just the charge of the ion. And then our other one that's sort of our good friend is water, +1 for hydrogen and -2 for oxygen. So find the easy ones first if you want to sort of build some momentum. And then the rest of them we have to go through a little bit more carefully to find out the oxidation numbers. So for MnO4 minus, we have oxygen in the formula. So we would assume that oxygen is -2. If we have 4 -2s, and remember that the sum now has to equal the overall charge, which is -1. So we have -8 from oxygen. So what do we have to add to that to get -1? +7. So we're going to have +7 for nitrogen. So it's a little bit of algebra either in your head or on paper to get +7 for manganese. Sorry, not nitrogen this time. If we go to NO, this one is fairly simple because oxygen in a covalent compound is -2, and that leaves +2 for nitrogen to make sure that they add up to 0. And then NO2, I think we saw that in the last problem as well. We have 2 -2s this time, so that means nitrogen has to be +4 so that they all add up to 0. All right, so again, for neutral compounds, the sum of the oxidation numbers equals 0. For charged species, the sum of the oxidation number equals the charge of whatever that ion is. All right, so that's what we have for oxidation numbers. And then our next step is to be able to find the ones that are changing between reactants and product side. So we see hydrogen is +1 on both sides, but if we look at manganese here, +7 over here, +2 over there. So we're going to draw a tie line between the ones because those are the ones that are losing or gaining electrons. So manganese is going from +7 to +2. Nitrogen we see goes from +2 to +4. Okay, so the ones that are changing, we want to mark those as being the ones that are either gaining or losing electrons, because the first part of balancing a redox equation is going to be to make sure that the number of electrons that are lost and gained ends up balanced. And the way we figure out the number of electrons for each of these is by looking at the difference in oxidation number. So manganese goes from +7 to +2, so that's a difference of 5. So that's going to be a 5-electron process. Technically 5 electrons are being gained. We don't really care if they're lost or gained. We just have to make sure they balance each other. And then finally for nitrogen, it's going to be, we care about whether they're lost or gained sometimes, not in this problem. I shouldn't say we never care. For nitrogen, it's going to be +2 to +4, so that's a difference of 2 electrons. So we have a 2 and a 5. How do we balance those two with each other, especially if we want to just keep whole number coefficients like we want to here? Yes, so we want to find the least common multiple of 2 and 5, which in this case is just the product of the two, which is 10. So if we double this one, that's going to make it 10 electrons. If we multiply that by 5, it's going to also make that 10 electrons. And so what that means is the two that are multiplied by 2, both of those have to get coefficients of 2. We have to adjust the coefficients on both sides. And then for this one, which is multiplied by 5, we get coefficients of 5 for both of those. Now to save yourself some time and potentially some frustration, look at what the question is asking you for before you decide to go all the way to the end. Now in this question, we do have to go to the end because we're looking for the sum of all coefficients, so we need to finish this off and figure out the coefficients for H plus and water. If we just asked you for the coefficient on either one of these 4 species, we could stop here because these coefficients are not going to change anymore. Once you balance the number of electrons, you stop with those ones and don't want to fix them anymore because then you're going to unbalance what you just did. But in this case, we do have to go to the end. So the way we typically handle this is water is going to be added to balance out oxygen, so we're going to do that first. On the left side here, we have 2 times 4 is 8 plus 5 is 13 oxygens. On the product side, we have 5 times 2 is 10 oxygens, so we need 3 more. Okay, so this time we already have some oxygen in this product, but we need 3 more to keep the same number of oxygen on each side. And now that we've added 3 waters, that now puts 6 hydrogens on the right, so we need 6 H pluses on the left. So that's typically the order we're going to do it in. We do oxygen first to make sure that the number of oxygens is the same on each side. We do water first, and And then once we add water, that's going to dictate how many H pluses we add to the other side, okay? So that's the final one, and then the sum of the coefficients is going to be 6 plus 2 plus 5 plus 2 plus 5 plus 3, which is equal to 23, okay? 8, 5 is 13, 15, 20, 23. Okay, good. Remember, if a coefficient is not listed, that means it's 1, so don't forget about your coefficients of 1 if they're there. All of these coefficients are not 1, but if there was no coefficient, you still have to count that as 1. And in this case, that's how we would go through it. So any questions on this one or balancing these in general? Yep.
So let's say we didn't have the same number of atoms. Like if you had like nitrogen and the other side you had like N2, then you would double the coefficients, right?
Yes. We don't have that in the next one either. So there's a couple ways to deal with that. So a common one would be, let's say you had, on one side you had Cr2O7 2 minus. On the other side you had Cr3 plus. There'd be other things on each side too. So this would be a situation where you have, this is plus 6 and this is plus 3. So each chromium is going to be gaining 3 electrons, but you know that there has to be at least 2 of them because there's 2 in the formula here. So my preferred method to deal with that is to put a 2 here first, which will remind myself that whatever the coefficients end up being, this one is going to be 2 times whatever the coefficient is over here. And then if you adjust them, let's say we end up finding out that we have to take, this is 6 electrons, and let's say we have to double it to balance the electrons. Each of these get multiplied by 2, so it's become 2 and 4, and not 1 and 2. So I like to start with that just to make sure I don't forget that there's going to be a different coefficient on each side, and to remind myself that it's actually 2 plus 6 is going to 2 plus 3, so that makes it a total of 6 electrons and not 3. It's 3 for each one, but there's 2 of them. So you don't have to handle it that way, but I think that's the simplest way to deal with it. All right, other questions? All right, one more, which is very similar. In this case, we're again doing sum of coefficients just to make sure we do the whole thing here. So we have chromium chloride, nitric acid, chromium nitrate. So the one difference here, as we go through this, we'll see is when we go through oxidation numbers, we're going to always start with that. We have a lot more in this case, unfortunately, and no simple ions to deal with, so we have to go through these more deliberately. So chromium chloride is an ionic compound. Remember, chloride is always -1 if it's an ionic compound, and if there's 2 -1s, that means the charge of the metal has to be +2. So for ionic compounds, the charge and the oxidation number are the same. So it's going to be +2 for that one. HNO3, I think we had earlier in one of the other problems. As we saw, it's going to be -2 for oxygen, +1 for hydrogen. That leaves 6. -6 plus 1 is -5, plus 5 for nitrogen, so we saw that earlier. In chromium nitrate, what I think is helpful for this one, again, is think about this as an ionic compound, which it is. So you have 3 NO3 minuses. So what's the charge on the metal then? +3. And then so nitrate NO3 minus, all we did was lose a hydrogen, so the other oxidation numbers don't change. We can verify that by thinking about that by itself, NO3 minus. You would again get -2 for oxygen. If you have 3 -2s and the overall is -1, you have to add +5 to that to make it -1 overall. So the charge of the ion, which is NO3 minus, has to equal the sum of the oxidation numbers, +5 and 3 -2s. And remember that the oxidation number cannot be greater than the group number. Nitrogen is group 5, so it's not going to go higher than 5. On the product side, we have also HNO2, +1 for hydrogen over here. So that's going to be -4, -3. So we have a +3 for nitrogen to make sure they add up to 0. Our good friend water is +1 and -2. HCl, +1, -1. Pretty simple as well. All right, so those are all the oxidation numbers. And then when we look at what's happening here, we see that for chromium, we're going from +2 to +3, so that's 1 electron. For nitrogen, we're going from +5 to +3, so that's 2 electrons. So we have 1 electron for one of them, we have 2 electrons for the other. And so how do we balance these? This one's fairly simple. We just put a 2 there. All right, so then this one we would put a 2 there, so we would get a 2 and a 2 in front of the 2 chromium species to make sure that those, we do the same thing on both sides. These ones are going to stay at 1 because they're already 2 electrons. So then when we write this out, we see that we have 2CrCl2 plus HNO3 goes to 2 chromium nitrates. Now in class when I did this type of problem, I actually ended up separating the HNO3 into 2 parts. That sometimes causes confusion, so I'll try it the other way here. Now we have, it goes on forever, H2O and HCl. So we have to balance everything else by inspection. So this is already balanced, this is already balanced, this is already balanced. The problem now, though, is that we notice that we need additional HNO3s, right? Because one of our HNO3s is going to get converted into HNO2. It's going to be reduced from +5 to +3. But then we also have additional nitrates that we need to supply the counterion for chromium nitrate. So if we have, here we have 2 times 3 is 6 additional nitrates plus the one that was reduced to HNO2, so we need a total of 7. So in class, as I said, I separated it out into 2 pieces and then recombined it at the end. But however you end up doing that, you end up with 7 HNO3s because we need one of them that gets reduced to HNO2 and then 6 more to balance these nitrogens here that are part of the chromium nitrate. Okay? So that balances the nitrogens. And then finally for water and HCl, we have to see what their coefficients are. So on the reactant side, we have 7 times 3 is 21 oxygens. And then over here, we have 3 times 3 is 9 times 2 is 18. 2, so we only need 1 more oxygen. 18 plus 2 is 20. We just need 1 more, so water gets a coefficient of 1. And then for HCl, we have 4 chlorines on the left, so we need 4 HCl's on the right. And then if we did that right, hydrogen should balance as well. So we get 1 plus 3 plus 4 is 7. 7 times 1 is 7. So in this case, I didn't separate them out because that seems to confuse people more than it helps them sometimes. So we just had to recognize that at the end when we were going by inspection to make sure everything else was balanced, that we didn't have enough nitrogen on the reactant side because of all these nitrates here, so we had to add 6 more to make sure that it was balanced on both sides, and then a total of 7. Only one of those is losing the electrons to go from HNO3 to gaining electrons to go from HNO3 to HNO2. The other 6 are just used to provide the NO3 minus counterion that's paired with a chromium 3 plus on the product side. So then I guess we asked for the sum of the coefficients here, which I did, so it's going to be 2 plus 7 plus 2. Remember, if there's no coefficient, that still counts as 1, 1, 4, so we get 9 plus 2 is 11, 12, 13, 17. Oh, yeah, because I can't read, or I didn't read. Just the reactant side, so we just need 2 and 7 is 9. All right. So that, in this case, I guess, well, it was important to get this one correct. So we had to still go to the end to make sure that everything was balanced in full. All right, that takes us to the end. I will stop the video now so that people don't have to listen to question and answer. But if you have additional questions, I'm not really tied up now, so I can stay